So today I'm going to give some details about how algorithms are going to be executed on an NMR processors. And the effective Hamiltonian that is implemented as a simple form. We'll leave out all the minor details and write down a kind of idealistic version, which is what is used for designing all the algorithms. So there is a term coming from the background static field, then there is a interaction between neighboring couplings, and then there is a radio frequency field, which I will just write as some combination of x and y with time-dependent interactions with the RF field. Okay. And all the algorithms are now going to be constructed using this set of operators. And I gave an example last time where this control Z can be decomposed as a product of these operators, or rather only the Z terms are involved in the transformation. And let me repeat that form. All factors commute because they all involve only the Z operators, and these exponentials are applied for a specific duration. In this case, it is all pi over 4 in terms of the rotation angle, and you have to generate this pi by 4 from the strength of the coupling multiplied by the time of evolution. Okay. So for example, the only two-body term is this first factor, and this can be produced by this interaction for a duration which, well, everything has to cancel out. So it is this is 1, 2. And remember that this interaction is always on. It's there in the molecule, and you can't change it or turn it on or turn it off or any of those kind of things. So if you let the Hamiltonian evolve by such a duration, these factors over here will cancel out and produce a pi over 4. Okay. So that is fine, but then you can't let these other terms or even a longer duration appear in the algorithm, because they will spoil all the effect of what is constructed over here. So the other factors need to be cancelled or adjusted. And this requires a kind of general method which goes under the name of refocusing. What refocusing essentially does, it creates a transformation which goes effectively backward in time. So some factor is produced by time evolution, you reverse it and then it will cancel out. But that algebra needs to be worked out, and I will illustrate it by giving a particular example of how this refocusing is done. So it so any extra stuff which gets produced, for example, applying this for a particular duration, whatever you don't want, you need to find a suitable sequence of pulses which will cancel it out. So for that, the particular operator which is easy to understand is, say, I define a rotation operator in direction x and on the first qubit. Okay? And this, by definition, is given a particular pulse duration, which is pi over 4. This x is coming because it's a rotation about x-axis, and the 1 refers that it is applied on the first bit. So take this as a definition, and now comes a particular sequence which is square of this operator multiplied by evolution under the z operator. A is just some variable or a constant which is held fixed. All the dependence of z on the first qubit is in this particular factor. This can be anything which doesn't depend on the first qubit. Okay. And then apply the same sequence again. And then the job is to work it out. Okay. So we have r square over here, so that can be easily evaluated, which is exponential of minus I x1. Pi by 2 makes life easy for calculating the exponential. Cosine is 0 and sine is equal to 1. So this quantity is nothing but minus I x1. Okay. So now we put it in this particular expression. So it is minus I x1 exponential of minus I t a z1 and another minus I x1 okay. So now we simplify it. You can do it in many different ways. You can expand it out in terms of sines and cosine if you want, but it doesn't really make much difference. It's much easier to just note that x1 is going to anticommute with z1. So when you take this across this particular factor, this is just going to become exponential of plus it a times z1, and then this factor is going to get squared, which is, well, you calculate whichever way you want. This is minus 1. So overall phase, which is not going to do much, but the result is that this sequence of operation gives the same evolution with operator a times z1, but the time reversed. So if you have accumulated some unwanted phases which are all the functions of z, you can undo them by inserting these operators, and these operators are just single qubit operators produced by these pulses of this radio frequency operators. So this RF pulses produce this operator Rx1 in whichever form. And the important point to note it is that this A becomes some constant between some fixed numbers like this pi over 4 or some arbitrary function of z whose index is different from 1, because x1 will commute with all the z where index is different from 1. So it can even reverse a sign of this kind of a term as well, because it's proportional to z. Whatever is here doesn't matter, and it will undo that part as well. So this is called refocusing, and it's used heavily to get rid of all the unnecessary factors which appear in the time evolution. The reason being that this particular interaction is always on. You can't turn it off, but you somehow cancel its effect by reversing the direction of spin in a certain sense. So this is the technique, and now you can write a generic algorithm by introducing whatever 2-qubit gate you want to implement, and then all this extra stuff which will cancel out the other factors.
So So these unnecessary factors always come from nearest neighbor interaction. Did I get
They can be any interaction. It can be a single qubit term or it can be a 2-qubit term also. The only thing is you are performing a rotation on one, and it can be any other function which is proportional to Z1. That's all.
the part which was always on was only nearest neighbor interaction?
Hmm?
The part which was always on was
This was nearest neighbor interaction only, yes. Because that is what all that exists in the Hamiltonian.
I think only so this should be only unwanted.
Unwanted terms coming from the Hamiltonian.
The
Whatever
part
is there in the Hamiltonian. If there are extra terms which are present, you need to cancel them. And that is because you can't turn off the coupling, but instead you reverse the direction of evolution.
coupling between neighbors.
Hmm?
Coupling between neighbors.
Whatever is there in the Hamiltonian. It can be used. Hamiltonian has only 1-qubit and 2-qubit terms. There are no other terms at all. So this is a very useful procedure.
Say we want to implement a gate rotation about Z1, and we use this to cancel the cancel the effects due to the coupling.
Yeah.
So wouldn't it also cancel the effect due to the initial gate, the gate that we wanted to implement? Is it okay?
Yeah, this, I mean, there are 1-qubit gates, but those are essentially instantaneous because the durations of this 1-qubit transformation and 2-qubit transformations are orders of magnitude different from the fact that this omega I and Jij are orders of magnitude different. So when you are implementing 1-qubit gate, you just ignore this. It's going to be small. But when you are implementing 2-qubit gate, you cannot ignore this one because it's going to happen at a much faster rate, and whatever happens, you have to cancel it. And that is done by this. So yes, this refocusing is used, but only to uh, tune the whatever the implementation of the 2-qubit gates. Yeah.
Cancel out the effect due to omega I, omega I Z, right?
Hmm?
To cancel out the effects of the single qubit rotations.
Yeah. Okay, so this is yeah. Essentially used for 2-qubit gates. For 1-qubit gate also, well, something which is needed, and that is they are all implemented in the so-called Euler angle decomposition scheme, because a general 1-qubit gate will be specified by some arbitrary axis and angle of rotation. But given the Hamiltonian, you have rotations available only about fixed axis. It can be either z or x or y, because those are the operators. You don't have linear combinations of axes available. So any generic operator for rotation can be broken down into a sequence of Euler angle rotations, which are about fixed axis. And that is also done. So And the particular decomposition in Euler angle is not unique, but again I can illustrate the idea very easily. So for example, consider one of the common operators which appears in lots of algorithms, which is the Hadamard operator, which is the sum of sigma x and sigma z. How will you implement it? If you geometrically try to understand what it is doing on a block sphere, you can say this is x-axis, this is z-axis, and what this operator does is it interchanges x and z. Okay. So it is actually a rotation about the bisector between this by angle pi, which will flip z to x and x to z. So it's not a rotation along this axis, but it's rotation about this bisector. How will you decompose it? In this particular case, the answer is rather straightforward. So what you can rewrite in a rather simple fashion is factor out one of these terms, and what you get is y plus identity z time y is equal to minus ix. And so now you can rather easily rewrite it. Z is a exponential of I pi by 2 times z, and I have to cancel, so there is a overall factor of minus I, which gives this, and this identity plus IY is I pi by 4 times y. Cosine and sine of pi by 4 will produce this 1 by root 2. So this operator can be now implemented as a pi by 4 rotation about y-axis, followed by a pi by 2 rotation about z-axis. That I can do with this Hamiltonian, and it's an example of this Euler angle decomposition. So you can play on this trick. So if this if you want to extend it, that this is only a particular combination of x and z, but suppose I have all three x, y, and z together. Very general. So what do I do? Well, I can first implement a z rotation, which will mix x and y so that it comes back to one of the directions, say x. And then this x and z I know how to deal with, just as in case of Hadamard operator. So it will be implemented by this form. So this can be converted from any sigma dot n to a scheme which will become z, y, z. Well, first I have to rotate along z-axis to get rid of y, and then this x and z can be merged into first operating by y and then operating by z, etc. So this shows, rather it's a simple-minded prescription to convert arbitrary arbitrary one qubit rotation about any axis to these rotations by some specified angles along fixed axis in the three-dimensional space. And at the most, you will have 3 factors, nothing more than that. So this is also a useful thing to keep track of. And the algorithms are all done automatically to include all those things. There are basically library routines available. So if you give a sequence of logic gates that you want to implement, the library will come out with the appropriate pulse sequence where all these fixed axis rotations are implemented and all these unwanted phases are all cancelled. It's all modeled with just this simple Hamiltonian that this you have to provide, and then it will find you the necessary sequence. There are actually some other tricks which offer shortcuts. So I can mention them as well. There are certain operators which can be implemented very easily in the NMR framework without going through all this complicated logic sequence, and one of this operator happens to be swap. Swap means you just want to interchange the values of 2 qubits. So what it does is if there are 2 qubits written in this basis of zeros and ones, you need to interchange these 2 states. The other 2 states don't matter. And this is a coupling, or it can be interpreted as a coupling between 0 and 1. And if you want to interchange them, then you can call this a transition. That this state goes to this state while the 2 0 and 2 1 components don't change. So this is a operation which can be performed by a transition selective pi pulse. Okay. Rotation by 2 pi will come back complete cycle. So if you sign a corresponding electromagnetic wave between these 2 levels, which is directly in resonance with the corresponding frequency, run it for half a cycle, it will interchange. And if you run it for 2 pi, it will come back to its starting point. And so you don't need complicated gate operation, you just need a direct this RF pulse which matches the frequency of the 2 qubits. And it will do this swap operations, and any general permutation can be built from this. With the sequence of swap, any general permutation operation you want to perform, you can just do it by these individual steps without going into a detailed decomposition in terms of 1-qubit and 2-qubit logic gates. What you want is these energy levels are addressed directly. Sometimes there are many other possibilities that you want to take this around. Maybe there is no direct coupling. You can go through an auxiliary level and still flip it. Which are some states which are not part of this description at all. There are some excited states or metastables. They can be intermediate steps as long as you can jump around from one to another by performing certain swap, you can take advantage of it. But an interesting application of this swap comes in when you want to perform an operation between 2 qubits that are not connected. They're far away in the register. Because this came fixed with the molecule, whatever you are using, and it has nearest neighbor connection. Suppose you want to implement a 2-qubit operation with the 2 qubits some distance away. How will you do it? There is no direct coupling in the Hamiltonian. So this can be taken advantage of. So long distance two-qubit operations can be performed by this sequence of swaps buried in the procedure, and it will use, well, I will have to just write it down in steps. So use your 2 qubits some distance far away. You can move only between nearest neighbors, and so you keep on swapping this thing along the chain till they come adjacent to each other. Then whatever execute the 2-qubit operation, because once they are adjacent to each other, you can take advantage of this J coupling, and then reverse the whatever swap sequence to take the qubit to their original location. This is not the only way of doing it, but it's a rather straightforward way of doing it. You wanted a long distance coupling. Well, you have to pay some price in terms of all these extra swap operations, but you can do that in a straightforward manner using all the structure which has already been described, and it gives you an estimate of how much is the computational cost. So, well, and the cost is basically nothing but the distance between the qubits, which comes from all the swaps they are doing. So yes, the longer distance 2-qubit operations are more expensive, but it is proportional to the number of qubits. So in terms of the polynomial scaling of algorithm, it is not a restriction at all. It goes up a little bit, but goes up only linearly in terms of number of qubits. So this is also done for uh, algorithms where there are 2-qubit operations at a longer distance. Just decompose it um, in a particular fashion and then carry out whatever operations you need. And all this jugglery, whatever it is done by a library. Yeah.
So we are talking about spin states here, right?
Yes.
So what are metastable states for these spin states?
There will be other labels of the nuclei which are outside the Hilbert space of this spin half Hamiltonian, whatever you describe. And even they are sometimes used as auxiliary in between thing, as long as you can take the population and bring it back. So they are there. With all the nuclei are quite complex set of atoms, and spin states are generated by the Zeeman splitting, but the other states are already there by the structure of the nucleus. If you don't want to use them, you stay away from it, but sometimes it is useful when you are trying to jump around between various components, because they offer essentially shortcuts. Can't go long distance very easily, but suppose there is a cleverly situated metastable state, you can cut down the propagation distance.
How exactly will they arise in the nuclear states, like in electronics, like lasers, with the simpler metastable states that we do?
Yeah, you have to study them. And for hydrogen, actually, there is not much because it's only one proton. But for carbon, there are other states available. Yes, there is a valence lowest state is a spin half, but the other excitations are there. Even for nitrogen, whatever oxygen, other atoms you use, there are other states available. All these various things, control operation, and also the Fourier analysis. that these operations are all very well understood. So what you have is essentially a software library, and all this jugglery. You give a algorithm at a top level, it will figure out what are the pulses, what are the controls you have to implement, what is the Fourier analysis you have to done. It's all done by a PC, which will actually be running the experiment. You don't directly turn any knobs because that is not as accurate. So you have to, well, accept this as one computer controlling the other computer in some sense. But there is a whole lot of industry which has been built inside it, not only for doing what you call quantum computation. NMR, the popular uses are in biology and chemistry, which have refined these techniques to a very high level. How to do this and how to save some time. So there are optimization and they go by all kind of various acronyms. I will just mention them. One of them is called GRAPE. Which is a short form of gradient ascent pulse engineering. Then, of course, there are so-called genetic algorithms which shuffle around various operations to cut down on the structure. And of course, these days there is a machine learning, which is also used to optimize some complicated operation into a more efficient set. Once you go through these techniques, the algorithm will look nothing like this original pulses which you have in mind. It is not even pulses, it can be just some continuous variation of magnetic field and some function of time, but it will do the job. And that is essentially the points. And what is the target is maximize the so-called fidelity of operation in a fixed amount of time. The time for the algorithm is fixed because the state is going to decay. You can't allow it to just go along forever, so you put a constraint that yes, the algorithm has to run in this much amount of time, and now it will tune everything to maximize the fidelity of operation. And all these algorithms do it. They are again available as some kind of library routines and part of the software run by the classical computer. It's just there first to design something, then you optimize it and let everything be implemented, and that has worked well. And to Well, there is one more trick which is needed, and that I will just give by quoting this well-known example, which was the first demonstration that yes, all this complicated machinery works, and that was Shor algorithm for factoring the smallest non-trivial product you can construct two prime numbers 15, leave out 2 because 2 is too easy. You don't have to look at the whatever number of digits at all. It's a binary representation. If the last bit is equal to 0, it has a factor 2. So that's too simple. But the next best thing is 15, and it was implemented with 7-qubit. This NMR processor, and the year was 2002. So this was actually among one of the first non-trivial results showing that yes, you can do quantum logic. Of course, not for arbitrary large register also, but a small processor, 7-qubit, it could do this particular job. And it was basically Shor's algorithm, essentially Fourier transform, which was the non-trivial part of it. But they had to take care of one thing, and that is a consequence of the so-called ensemble mode of computing. The experiments implement is not one molecule performing this, but lots of molecules doing the same thing in a statistical mixture. And what you get is not a result, but average over all the components in the mixture. And that kind of gets confused what are called probabilistic algorithms. There is already one averaging in the ensemble. If there is a probabilistic description of the result of the algorithm, there is another average over there, and the two get mixed up and you can't separate it out. So what you need to do is convert the probabilistic algorithm into a deterministic algorithm if you want to use this ensemble mode of computing. So the algorithm is some amount of post-processing which is done later to extract the answer from this probabilistic description. You have to put it inside the algorithm itself till the algorithm becomes deterministic, and then run the whole algorithm in the ensemble mode. So there is a little bit of overhead. All this post-processing goes in, and in particular for Shor's algorithm, uh, there is a probabilistic description. Okay, so that had to be eliminated when this experiment was done, and the variables which appear is what we want at the end of the algorithm is a estimate of this periodicity, which is generally labeled by R, uh, and what the Fourier transform gives is a ratio typically written as S over R, and we don't want this. So whatever is needed to convert this S over R to R, it is executed as part of this particular quantum ensemble algorithm, and then you read only the value of R at the end of the execution. So this is a caveat, but it's needed because of this ensemble nature of computing. So yeah, this is a kind of story. Of course, there is one part which I have left out and which I have to bring it back. That is, how is this ensemble mode of computing actually used in practice? Because you need a quantum state, and this ensemble is a mixture. It is not a pure quantum state.
What do you mean by converting the probabilistic algorithm into deterministic?
Probabilistic answers generally produce
It's like
a result which is a distribution. Several possible values with some particular frequency of occurrence. And what you are interested in is actually not that distribution, but a specific answer. And this is the example for Shor's algorithm. When you run a quantum Fourier transform, it will generate various values of S over R, where S can be any integer and R is the fixed period. And if you do that, you will get a whole distribution over various values of S. But that is not of interest to us. What we want from the factoring algorithm is the value of the periodicity. So there are certain classical steps of the algorithm which Shor described, which converted this S over R to R. Now what this means that those classical steps you have to implement in the quantum processor to make sense of the ensemble averaging. Of course, it is easier to do it classically, but this is a penalty you need to pay because you can't do two different modes of averaging and combine them. All the answers will get completely mixed up and you will not be able to get a definite result.
Can we say that it's kind of purifying some ensemble representation? Like S over R, we obtain some statistics of it, right? So we are kind of purifying it into some quantum language.
Not purifying it, it's just it's a classical distribution. You are just trying to do certain steps which are done classically, but now those you want to implement in a quantum algorithm. Classical one is more stable and more efficient, but you have to give it up, because otherwise the situation of this ensemble implementation doesn't work out with it. So it's in some sense you are paying a penalty. What could be done classically, you are trying to do with a quantum uh, dynamics, and it's not as efficient. Okay. So the important step for implementing all the algorithms is based on this particular concept of pseudo-pure states. Okay. So what I have talked about all the time and this Hamiltonian, etc., etc. So the general ground state of this Hamiltonian, if you remove all this RF field, is defined by the values of Z, which is just various energy levels, occupied or unoccupied, and there are a bunch of levels with different energies, then that is completely thermal distribution by the Boltzmann factor and whatever it is, 1 by Z e raised to minus beta h. So this is what you get in the experiment naturally every time. This is not a pure state. And pseudo-pure state is a technique to construct a state which looks like a pure state from this particular distribution. And what does that require? Well, you have to go back and remember what are the properties of a pure state. Density matrix, it has only one eigenvalue, which is equal to 1, and all the eigenvalues are 0. So it's a diagonal density matrix, but 1 and a bunch of 0. Here it will be a diagonal density matrix with all kind of numbers given by the Boltzmann distribution on the diagonal. So then this is kind of well known. There is a description rho square equal to rho for pure states, eigenvalue are all restricted to 1s and 0. How do I get this from that? Otherwise, the quantum algorithm doesn't make sense. So what is done is a combination of two ideas. One is one can make linear combinations of different rows, different distributions. So this is one ingredient. Is a proportional to identity plus you are going to use multiple choices of this distribution so that the sum of all those various distribution looks like this. Why can you do this? The second feature is that the I does not evolve or produce measurement signal. Because of all the various operations we write down, we apply either a unitary operators, then U times I times U dagger is identity again, and the measurement was responding only to the traceless part of the structure. The identity in that free induction decay produces no signal. So if I have something, adding this I or removing it doesn't matter, and this R will give then the actual dynamics and the signal. And the third feature is that all everything that you can observe is linear in row. And so if you take different rows and add them together, completely legitimate. Because it's a sum of the different results will still give you the correct expectation value. The point is I able to take multiple different choices of row and add the results together to get the correct expectation value. If I look at only one component, it is not going to give me the correct answer, but the linear combination will produce the required result. So this is what is done to construct these pseudo-pure state. Pseudo-pure state is nothing but this particular combination, pure state plus identity. Okay. So now there are various strategies, and I will give examples. One of them is called temporal averaging. And it literally takes different distributions, or why it is called temporal is because those distributions are created one after the other in NMR experiments in the function of time. You take these multiple experiments, you average the results, and that has the desired property. So what are the things that you average? Yeah. Best thing is to just give an example. Consider a 2-qubit system, okay? With this Boltzmann distribution, rho is, I will only write the diagonal elements, some A, B, C, D came from whatever the energies of this state is. So from this distribution, I will construct new distributions, and the easiest way to construct those new distributions. By applying the swap operation, they just take that particular transition frequency and apply a pi pulse. It happens very quickly, and you can do it uh, without perturbing any other thing, the very short pulse. Okay. So I will apply it selectively on various levels. So if I apply on these two, I generate B and C getting interchanged. Then I can interchange C and D as well. And then I can interchange B and D by applying suitable swap pulses. And then is some part of identity. If I add all this three things together, there will be B plus C plus D appearing in all these things. I can subtract it out. And A will add up whatever state is. And this has the required form. It's a pseudopure state. So what I do is I generate 3 experiments. Each one starts with some thermal distribution. I first apply this swap, one of those 3 types, run the whole computation, one after the other, then take the results of all the 3, add them together, and then whatever observable I want to calculate, it has the necessary value.
So we are doing swap operation between 2 pure states or between 2 qubits?
Between 2 energy levels.
So each
It's directly in the Hilbert space.
so one is specific energy level, so correspond to one pure state. Not necessarily.
You don't have to interpret in terms of states at all. These are energy levels and the corresponding occupancy. It's completely classical in some sense, the Boltzmann distribution. How many atoms are there in which energy level, that's all.
So energy levels also can be swapped. So, okay, that is the simple swap operation.
Levels are fixed by some convention. Once you define a Hamiltonian, it has some labels of 1, 2, 3, 4, whatever convention you choose. Don't change it. Then all you can change are the populations in various levels.
These swap operations are changing population.
Yeah, so they are changing populations between 2 levels. Whatever the transition selective pulse you applied, pi pulse, and it will interchange the populations.
So, where do these pure states sit in the algorithm? So, like to begin with, I have some thermal state.
You have to run the algorithm 3 times with different swap operations at the beginning.
So, the elements A, B, C, D are fixed, right? So, then do they define the labels of the pure state, right?
They are just the populations of various energy levels. I took a 2-qubit system, so there were 4 energy levels. That's all. So this is one of the tricks, and then there were some alternates for the pseudopure states which were also constructed. Well, some of them were actually designed and implemented in Anil Kumar's lab here in the same time, somewhere around early 2000, and demonstrated that they all work. So there is um, some related thing which is called spatial averaging. This is temporal in the sense that you are running 3 different experiments and adding them up afterwards. What spatial averaging does is these populations of labels can be modified by changing the background magnetic field, because the background magnetic field is what was going to produce this e raised to minus beta h structure. So what the spatial averaging does is apply different magnetic field in the same sample at different locations. The sample is an ensemble, something in a test tube, but you vary the magnetic field across the sample. And if you do it in again a cleverly designed fashion, what you have to do is take the whole ensemble average, which is coming from the whole sample, but it is coming from regions where the magnetic fields are different, and that rearrangement is such that again you will end up with a pure state, because in different regions there will be different orderings of these populations, and when you add them up in the whole ensemble, you have the correct distribution. Of course, you have to design the magnetic field cleverly depending upon what state you want to construct, but for certain situation it is possible. So great, there is a magnetic field gradient is applied across the sample, and then so here you have to design this magnetic field gradient depending on the terms in the Hamiltonian such that various possibilities coming from different regions. When you add them up, you create a pseudopure state, and then the experiment will be run only once, because ensemble average will do all the mixing of the density matrices, but you have to be very specific about how the gradient is calculated, which is applied across the sample. Okay. So that is called spatial averaging. And third one, which is actually more interesting, it's called logical labeling. And the idea here is that, yes, you have this distribution in the Hilbert space. You want to rearrange the distribution so that inside a subspace, the population will look like a pseudopure state. Not on the whole state, but in the subspace. So you will generate the full distribution according to the Boltzmann formula, but then only work in a subspace of the whole system. You don't go outside that subspace at all. Okay. So the structure of this is again illustrated by an example. And the subspaces will be then be labeled by some manner, and that labeling is called this logical labeling. That you are not going to work with all indices, but some indices will be kept fixed, which will define the subspace, and the remaining indices will be varied. And again, the example is easy to construct in a case where the nuclei are, when the various nuclei involved are essentially the same. So let me take an example where are three nuclei which are the same, say hydrogen. That will basically mean that the energy levels are more or less the same. There might be a little bit of chemical shift, but the major part is essentially identical. Then what will be the distribution? So it will be given by this Hamiltonian, the standard one, but I should write some convention which is simple enough. Okay. Some coefficient and this 1 and minus 1 are the strengths of the Zeeman splitting for spin half. So the population will be some component of identity plus that term coming from beta times h, which can be written as some magnitude and plus and minus of the two levels. With this, I use the usual Taylor series expansion, which is available in all the NMR experiments. The coefficients are rather small. And I have three nuclei of this type, so each one will behave like this, and the tensor product of three of them will denote the total density matrix. So now I can expand this thing out. Okay. So it will be identity, and I will keep only the term which is linear in A, they call the coefficient are small, and then there will be tensor products of these objects, and I have to write down the whole matrix with some convention. So the usual labeling, okay, let me put that. There are 8 states. We'll order them the usual binary numbers with zeros and ones, and then you count what are the values coming from this +1 and -1, and you will immediately come out with a rather simple looking pattern. Which has all these binomial kind of coefficients going from 3 to -3. Yeah. So this does not look anything like that pseudopure state 1 and 0. Okay. But now I can split these labels in a clever manner. So there are some labels here where one of them is 3 and the other ones are -1, and that combination is traceless, just like whatever was over here. And then there is a other half which is kind of complementary. It's a 1, 1, 1 and -3. And the point is that each one of them gives a pseudopure state. One of the population is different than all the rest, and then there is only identity. Means you can shuffle around parts from here to identity, vice versa, doesn't matter. So what logical labeling will do is take this 3-qubit system and do all the experiments only 4 states which correspond to a 2-qubit subspace. And don't touch the other half. Or you can do both ways. You can do something on one half, do something completely different on another half if you want. Just make sure that they don't mix with each other. Okay. So this will also do the job, except that from a larger Hilbert space, now you are working on a smaller Hilbert space. So that is where you paid the extra price about how much extra effort is required. But that is completely okay. And now you can actually see one of the limitations of these NMR experiments, which I mentioned earlier, how it comes back in this pseudo-pure state implementation, that there is a kind of limit of how many qubits you can include in the implementation. And the pseudo-pure state actually gives you a quantitative formula about what is the strength of the signal. So one can ask, what is the magnitude of the pseudo-pure state where it is the size of this element? The other stuff is all 0. How big it can get? And in all this implementation, it behaves like n times 2 to the power minus n, or n qubits. The 2 raised to power minus n is coming just because trace rho is equal to 1 and there are 2 to the power n states. And this n is about as large a term as you can get by doing all the linear combinations of multiple qubit signal. It is a 3 in this particular case. It is whatever 3a minus b minus c minus d over there. But it's a linear combination of populations all put together in the one of the location, and it can get a value up to n. It cannot do much more than that. And that means that these NMR experiments, as you increase the number of qubits, the signal strength is falling very rapidly, and maximum limit is essentially comes from these results. So well, it depends on what is the instrument's capability in terms of detecting the signal, and there is an experimental number here which I can quote. You need about 10 raised to 8 or more molecules to see the signal in a detector. Because a single molecule, the signal is too small. So if this is the strength of the ensemble, you need and that basically tells you this one is falling off, how far you can go. And basically it limits about 10, and if you push your luck, maybe about 12 qubits. You can't do much better than that. So that is roughly the story of all things which the NMR can do and how far it can go. And it has been useful to demonstrate lots of principles. In addition to that, lots of these optimization techniques which have been explored. I had mentioned something earlier, also something called bang implementation, which cancels again by time reversal certain unwanted effects. There is something which is called a dynamical decoupling, which will remove the environmental error by clever choices of all this design of pulses, and those methods have now been extended to other platforms as well. But there was a lot of things available and testable. That is the important part, and that were done with this NMR machinery. There are still some things more which have been done, but I will talk about it in the next lecture. But as far as the implementation of algorithm is concerned, this is more or less a complete story.
Sir, how we get this rho 1 plus rho 2 plus rho 3 equal to this last line? That was just addition or something else?
What?
How did we get the last line?
Add these three numbers.
So minus sign, minus b minus c minus d.
Yeah, there is some coefficient times identity which I have taken out.
So that term also depend on ABCD.
That will also depend on ABCD.